Let's finish this example on Green's theorem. In the previous video, we showed that the integral around c of f dot over ds was equal to 8/3. That was the left-hand side of Green's theorem. Now let's see that the right-hand side gives us exactly the same answer. Now the vector field f is given by y comma x squared. And remember that we refer to the first component as m and the second component as n. So on the right side of Green's theorem, where we take dn dx minus dn dy, that'll be the derivative with respect to x of n, which is x squared, minus the derivative with respect to y of m, which is y. So that's 2x minus 1. So the right-hand side becomes the double integral over r of 2x minus 1 dA. Let's see if we can set the bounds for that, for this region R. This region is both vertically simple and horizontally simple, so we could slice it vertically or horizontally. I think that we'll find it a little bit easier to slice vertically, because this curve is written in form y equals already, and notice that it's a fairly nice polynomial. If I were to slice this way, I would have to solve for x in terms of y, and that would give me square roots, and that seems like an unnecessary complication. So my integrand is 2x minus 1. And since I want to slice vertically, I'll be putting dy on the inside, dx on the outside. Now coming in from the bottom, this segment enters on y equals 0. So my lower bound for y is y equals 0. And it exits on the parabola, y equals 4 minus x squared. So those are my bounds for y. And for x, I go from the smallest value of x in the region, which is x equals 0, to the largest value of x, which is 2. So this is the integral we need to carry out. So let's start by integrating with respect to y. The 2x minus 1 is treated as a constant, so I have 2x minus 1 times y, taken from y equals 0 to y equals 4 minus x squared. This will be the integral from 0 to 2 of 2x minus 1 times 4 minus x squared minus 2x minus 1 times 0. So now to finish integrating this, we need to multiply this out. So we'll FOIL it out, and then we'll integrate term by term. So this is the integral from 0 to 2 of multiplying 8x minus 2x cubed minus 4 plus x squared. There are no like terms there, so we'll just integrate the polynomial term by term. The integral of 8x is 4x squared minus 2/4, so that's minus a half x to the 4th, minus 4x, plus a third x cubed, all taken from 0 to 2. Unfortunately, I've run out of space there, so I'll continue up here. Plugging in the 2, I get 4 times 4, which is 16, minus 16 over 2 is 8, minus another 8, plus a third of 8, minus, when I plug in 0, I get all zeros. 16 minus 8 is 0. Look at that. I get 8/3 for this side of Green's theorem, which was indeed equal to the other side. So Green's theorem guarantees that the two are going to be equal, so it often lets you convert one integral into another one that might be easier. Now, much of the time, the easier side is going to be the area integral because you only have to do one of them. An exception to that, though, is that, actually, let me say this isn't an exception. A special case of that, which is especially nice, is when dn dx minus dm dy is equal to 0, in which case the right side is going to equal 0, and you don't even have to carry out any integration at all. And notice that that is exactly the case when your vector field has a potential function, when your vector field is exact.